We are at 10 o'clock Pacific time. Good morning, afternoon to some, and welcome to today's webinar, Chromium Compliance with RCF, Proven Groundwater Treatment Strategies from ATEC Water. I'm Norvin Edson, and I'll be managing things behind the scenes today just to make sure everything runs smoothly. Before we get started, a quick couple of housekeeping notes. We have time for Q&A at the end, so please feel free to type your questions into the Q&A panel at any time during the session. This session is being recorded, and we'll share the recording with all registrants after the webinar. Now, I'm pleased to introduce our presenters today. First, Steve Green, Chief Commercial Officer at ATEC Water Systems. Steve brings over 20 years of experience working with municipalities and engineering firms to implement cost-effective, practical water treatment solutions with a focus on regulatory compliance and operational efficiency. Joining him is also Lee Odell. He's Chief Operating Officer at ATEC Water Systems. Lee has more than 35 years of experience in municipal water treatment, leading projects across the US that address contaminants like iron and manganese, arsenic, chromium, and PFAS. And with that, I'm going to hand it over to Steve to get us started.
Great, thanks, Norvin. So as Norvin noted there, we're ATEC Water Systems. Steve Green, I'm Chief Commercial Officer, and my partner here, Lee Odell, is our COO. And just of note, Lee is the guy that literally wrote the book on groundwater treatment. So if you've looked at the AWWA publication, Treatment Technologies for Groundwater, Lee is the author of that book, and significant experience in the groundwater treatment arena. And we're coming to you from ATEC Water Systems. So we're a small business based in Hollister, California. We're about 25 or 30 employees. And you can see a good part of our team here in the right side photo. We took this during our quarterly meeting recently. So today we're going to go over background and regulations on Chromium, a little bit about ATEC. And we're going to keep this part brief so that Lee can focus. I'll be handing over to him for this section 3 about chromium treatment. So background and regulations on Chrome 6. So Chrome 6 is a naturally occurring contaminant. It exists in the rock that's on the surface and underground. So it can show up in our groundwaters just because of that natural presence. It can also be present due to industrial uses, certain types of industries, right, that produce that as a byproduct. And, it is considered a known toxic contaminant in drinking water and has some pretty serious potential health effects, ranging from cancer, digestive system issues, liver and kidney, reproductive issues, as well as skin lesions. So, certainly something to take seriously here, which is why it's regulated. And as water industry professionals, right, we need to take this seriously and come up with the right treatment methods. On the federal level, chromium is regulated as an MCL, total chromium, which is a combination of trivalent chromium as well as hexavalent chromium in total. And if the tap water exceeds this level, that water provider is required to notify its customers. But where the regulations stand right now, they are not required to implement a treatment system. That is fairly different than in California, where chromium is now regulated, and it is required that water utilities that have chromium over a certain level have to treat for it. So California actually originally adopted those regulations as an MCL back in 2014 and set that specific to chromium 6 at 10 parts per billion. Now, there was a little bit of resistance from different utilities in California that didn't believe that they had done an adequate analysis of what that treatment requirement would mean for different utilities in California. And so it basically went through a legal process in the courts, the state courts of California. It ultimately it was invalidated by 2017 that was a required treatment. And so, a few water utilities, we'll talk about one of those later in the webinar, did implement treatment during that time frame. But by and large, most that looked at it, given the time it takes, right, to study and engineer and implement a treatment system, most did not get that completed by 2017. And so a lot of those projects went on hold. And, um, and then in April of 2024, then it was readopted, and it was readopted at the same level, focused on chromium 6 at 10 parts per billion. And so that became effective October 1st of last year. And then, depending on the size of the system, there's a different deadline that California utilities have to meet to have their treatment system in place for chromium. And so you can see that here on this slide, basically starting with the largest systems by about 13 and a half months from now, right, they have to have their treatment systems in place. Then as you step down to a little bit more of a medium-sized system, they have another year to comply, taking that to October 2027. And then, much smaller systems, then they have yet another year to comply, taking them to 2028. So certainly as a treatment solutions provider, we are seeing some activity in the market. We're getting set to pilots with several larger utilities that have this first deadline that you see here of October 2026. So thinking of the time it takes to pilot a system, verify performance, get that system ordered, design around it, take care of permitting, get a contractor on board, and ultimately construct, right? This is a pretty tight timeline, the length of construction that happens here. Wouldn't be USA without a quick reference to pop culture. And so if anyone has ever seen the movie Aaron Brockovich, is actually based on a true story about a community that had significant contamination of their groundwater by chromium. And it was related to, I think, some corrosion resistance treatments that were undertaken by PG&E with their towers, right, their electrical towers. And there was a basin that had a lot of chromium in it, ended up in the groundwater that supplied this community. And so there was a lawsuit associated with that, which is dramatized in that movie. And ultimately, there was a settlement at that time that was actually the largest sum ever paid out in a direct action lawsuit. And so that film in the year 2000 focused on this. And you can see the left photo here is the actual people that undertook that lawsuit, and then the right side here, you see the actors that were involved. So with that, I'll talk a little bit here about ATEC, just so you know our background. So we've got about 500 systems in the markets, all along the West Coast and a little bit in the Midwest US. About 500 systems total, including about 80 in California, where these chromium regulations are active. We do have one customer that does have an active system with chromium that we'll talk about a little bit later. We've assisted others, but they did not implement because those regulations were put on hold, and now we're back active with some of those. Our business started in the early 80s, focused on the irrigation markets, developing filtration systems. In the 90s, the business was pivoted to focus on the water utility industry. And so we've been addressing groundwater contaminants for water utilities now since the mid-90s. In 2022, the company was purchased by Cadiz. So Cadiz is a private water wholesaler based in the Los Angeles area. Came to work with ATEC through some systems they're developing, and it was a good fit then to acquire the company. And so since the company's come under Cadiz ownership, we've actually been pursuing much larger projects. We've recently shipped the Central Utah Water Conservancy District. It's an iron and manganese treatment system with a 60 MGD capacity, expandable to 80 MGD. That system will start up here in about a month. Once it's up and running, we believe that's going to be the largest iron and manganese treatment system in the entire United States. We've also taken our business nationally, working with independent manufacturers representatives, and partnered with a company called Setco in PFAS treatment, which is another part of our product portfolio. And now 2025, right, we're working, with several water utilities in California to figure out the best way to treat their chromium contamination. So our business, we manufacture and fabricate these complete skidded water treatment systems for the different contaminants you see listed here on the right. Iron and manganese is obviously one of the most common of these, as well as arsenic and PFAS and then chromium. We do address these others that are less common in groundwater, but nonetheless important to address. And systems that address anywhere from 20 gallons a minute all the way up to 60 mgd and larger. Our systems ship completely skidded. So you've got your inlet piping, your outlet piping, if there's backwash piping, and then the control system. So much like a manufactured house, we're able to do this in our factory very cost effectively, ships to the site and it's ready to go. The contractor makes 3 piping connections, as well as a control, power, and SCADA connection, and they're ready to go. And so we do 14-inch 14-inch diameter filter vessels, 18-inch, and then going up by 6-inch increments up to 48-inch. We match that to the system flow. We enable interfilter backwashing, which makes the overall infrastructure costs very effective for the entire site. And we bring that to the market. And again, we address systems of all sizes. You can see a small arsenic system here in California that treats 20 gallons a minute. You see a 15 mgd system here in the center. You see a 60 mgd. So it's very modular, it's very scalable, and we help utilities of all sizes. We do all of our own fabricating and build these systems completely ourselves. By doing so, we're able to be very cost efficient and have a great quality control. And so we're providing very reliable and very affordable systems to the market. We do pilot testing to help utilities validate the right treatment method and the right sizing of these systems. Endeavor to always figure out the highest loading rates to the media that's used for each contaminant that's still safe, right? In doing so, we know we've de-risked the project, it made it very cost effective for that utility. Higher the loading rate, obviously the smaller system that's possible to use, which saves that utility money, and ultimately the customers of that utility have more affordable rates. And so, there's always an initial design process, there's a consideration of potential technologies, and then you have to figure out what is the preferred technology. So if we're identified as a potential technology, there's a decision to pilot. We bring our pilot trailer to the sites. Whether it's iron, manganese, arsenic, or chromium, we can complete a 2-day pilot that will provide adequate de-risking of the treatment system, design criteria needed to then, design that full-scale system. And so we provide a pilot report that's got those design criteria, and then that utility has the opportunity to either pre-select or pre-purchase that product if there is a tight timeline, and they can have their consulting engineer focus on this exact technology. It makes that whole process very time and cost effective. And then, our supplier structure here as a company that's able to pilot and then, take that right through to the system design, do that all in-house. We're BABA compliance, we're AIS compliance, and we're basically delivering a very cost-effective value chain to the market here. We are a for-profit business, so there is one markup here associated with our company. But a lot of our other alternative suppliers we're aware of, they don't necessarily make their own treatment vessels, right? Sometimes that's outsourced. And so you do have another entity involved. You have another shipping step. So those lead times can be longer. You've also got another structure of overhead profit built into that sale. And so it may not be as cost effective. So just food for thought as you consider who your supplier is for chromium treatments. Make sure that you're getting the best deal. We can do containerized systems. Oftentimes on a site, it becomes expensive to build a custom building on site. So we do offer containerized systems. And with that, I'm going to hand it over to Lee to talk about treatment.
Okay, thank you, Steve.
Yeah.
There are a number of different ways to remove chromium from water. In California, there are listed 3 best available treatment, or BATs. They include reduction, coagulation, filtration, anion exchange with wheat-based anion resin. That's a replaceable resin, so you use it till it's used up and then replace the resin. And anion exchange with strong base anion resin, which is a regenerated resin. So you apply brine periodically and dispose of the brine. I'm mostly going to talk about reduction, coagulation, filtration. It's often, almost always, the low cost option and a pretty simple to run type system. Uses readily available technology, things that people are very familiar with. There's a reduction step, and then coagulation and filtration after that. Residuals are oftentimes easier to handle than especially the brine disposal. So I'll talk about that first, and then give you an idea of the comparison with ion exchange towards the end of the talk. So traditional approach to reduction, coagulation, filtration was really to provide reducing chemical, ferrous chloride or ferrous sulfate, provide a reaction tank for that to occur, and then oxidize that that reduced material with chlorine or air, and then filter out those particles or remove the particles in the clarifier, followed by a filtration segment. That's a typical surface water kind of approach to drinking water treatment. It requires a lot of infrastructure, a lot of operational oversight. You generally may have to pump between stations to get all the head. So what we focused on back in 2014, 2015 was trying to do everything in a pressurized system. So we developed basically a completely pressurized, very simplified approach to reduction, coagulation, filtration, where we add our reducing agent, either ferrous chloride or ferrous sulfate. We provide a reaction tank for that reduction to take place. And then we add an oxidant. And depending on whether we're using air or chlorine, we may need a second reaction tank for that to occur. But then we go right on to the filters, and we found because we're using an iron-based reduction chemical, that we actually get better removal of the reduced chrome and the iron together than if we were just trying to reduce the chrome with stannous chloride and filter it out without iron present in the water. So I'll show you some results that we have from a bunch of testing here. So how does it work? Very, very simple. We add our reducing agent, ferrous chloride or ferrous sulfate. They both work essentially the same effectiveness. So which product you use generally is, the customer preference, what's most available, least cost, Maybe there's an issue of chloride to sulfate ratios that somebody might want to look at from if there's a lead concern in the system, but they both work very well. So we add that reducing agent. We reduce the hexavalent chrome to chrome 3, and that chrome 3 then is much less soluble than the hexavalent chromium. So it comes out of solution, and then we are also adding an oxidant to oxidize the ferrous chloride or ferrous sulfate to a ferric. And once that iron precipitates, we get some co-filtration or co-precipitation with the chrome 3 and do a more efficient job of filtering it out. So case study, this system has been in place for about 10 years. Pilot testing occurred back in 2014, and the system was modified in 2016 for hexavalent chromium. It was initially an iron and manganese removal system, and it included just chlorination followed by manganese dioxide filtration at a loading rate of about 8 gallons a minute per square foot. The California Water Service Company and consultant went in, pilot tested ferric chloride reduction in front of it, and then chlorination right after that, and found they could get great hexavalent chromium removal. That facility has been operating continuously for the past 10 years. The backwash, in this case, goes into a backwash tank on site here, and then into the sanitary sewer for them. We have done a bunch of testing with reduction, coagulation, filtration to try to optimize the process. In initial pilot testing, we used pipeline contactors to figure out how much reduction time we needed and what kind of dose of chemical we needed. In the most of the pilot testing that we did that I'll show you, we were using air as an oxidant, but you can use chlorine as well. In fact, the chlorine oxidation is quicker, so you don't really need a second contactor for that to occur. But the process flow diagram is here. We do the reduction. We have a contact tank. We add an oxidant, a little more contact time for air, and then backwash or run through the filters after that. So some pilot testing, extensive pilot testing we did starting in 2015, actually went all the way through 2017 at the Cadiz site in California, using the contactors on the pipeline. Very similar process that I just walked through. We found we were getting from raw water hexavalent chromium concentrations of about 20 parts per billion, about a 90% reduction. There was also a little bit of arsenic in the water, and surprisingly enough, we were getting about 70% or better reduction of arsenic as well. Because we were reducing, we weren't really expecting that, but we consistently saw it for throughout the pilot testing. So this graph shows in 2015 the removal of total chrome and hexavalent chromium, as well as total arsenic. So when we reduce the hexavalent chromium to trivalent chromium and we filter it out, it's not just the hexavalent chromium that's getting removed, but total chromium as well. We looked at different doses of ferrous chloride and found about 1.5 milligrams per liter was optimal condition. This may vary from site to site, but that's a good starting point for a lot of systems. We also looked at contact times, and found the reduction of hexavalent chromium to trivalent chromium happened pretty quickly. So 2 minutes of reduction time, we were able to get almost complete conversion, complete reduction of the hexavalent chromium to trivalent chromium, and additional time didn't really give us much additional benefit in that case. We built a 50 gallon a minute treatment system at that same location after we did the initial pilot test, ran it for 2 years, collected hundreds of samples. We did some testing initially, found about 95% removal of hexavalent chrome, 91% removal of total chrome, about 80% removal of arsenic. And then we tried adding a little bit of filter aid polymer, ran it for another 6 months, and demonstrated we could get much better removal, not of hexavalent chromium, a little better removal of total chromium, and a little better removal of arsenic as well. So this is a tiny bit of filter aid polymer that we use. It was a dose of less than 0.1 milligram per liter, typically about 0.05 milligrams per liter of filter aid polymer. So from, excuse me, my slides are bouncing around a little bit. From the pilot testing, we showed that reduction coagulation is very effective for chrome. We also noticed, decent removal for arsenic in that system. Short pipeline contact times worked for air, and air oxidation was effective as well. We also know chlorine oxidation is effective. We don't need a second reaction tank if we use chlorine, so that's something to keep in mind. And a ferrous chloride dose of about 1.5 milligrams was adequate. Polymer addition helped. The residuals from this reduction coagulation filtration is a backwash system, so we're going to get frequent, maybe every 12 to 24 hour backwash of the filter. It's going to have 100 or so milligrams per liter of TSS in it. So the chrome will be in the chromium 3 condition. So where possible, we can discharge that to sanitary sewer. In some places, we may have to build a backwash tank, and that gives us either the ability to attenuate the flow into the sanitary sewer, or we can do recycle operations as well. The sludge can generally go into a roll-off box or some other dewatering mechanism. And backwash, we can do settling and then recycle, or in some cases, we may want to treat the recycle line with an additional filter as well. So lots of options for backwash water. We can help size everything and talk about options for that as well. At the Cadiz site, we did residuals testing. At that site, we were backwashing. We did a sand drying bed. We tested the dried sludge from our reduction coagulation filtration for both the California wet test and the TCLP test. We easily passed the TCLP test for both chrome and arsenic. The wet test has 2 parts. The first part is how much of the contaminant is in the sludge, and we were pretty close to the limit for the TTLC. We were at 2,200 milligrams per kilogram. The limit is 2,500. But the leachate part, we passed very well. So the issue here is if we use enough ferrous chloride or ferrous sulfate, and we have enough iron in the sludge, this won't be an issue, and the leachate part isn't a concern. So there is potentially a pathway to have a non-hazardous backwash waste or sludge from this process. An example of sizing these systems, we have design tools that we use and are happy to share with you. When you look at these systems, we sized contact tanks. So in this case, we're using our 48-inch tanks, and we design it to a contact time. In this case, I've got 4 minutes. So this is an example of a system that is using air. We need about 2 minutes for reduction, 2 minutes for air oxidation. If we went to chlorine, we wouldn't necessarily need both stages of that. The filtration vessels, in this case, we're looking at the filter loading rate, which we identify from pilot testing of about 6.7 gallons a minute per square foot. Backwash frequency, we also determined from pilot testing, gives us our backwash volume, and we can look at recycle rates based on that. And then we can look at potential use of chemicals. So you can size a 30-day supply of chemical on the site. And we can prepare cost examples for you. So in this case, we've got both a system using air and a system using chlorine for 2,000 gallons a minute. I've highlighted the chlorine system. So it's got 6 vessels for contact tanks and then a 20 vessel skid for the filters with a equipment cost of $877,500. And that's very typical for our types of systems. Just a quick comparison here for an ion exchange system. So this may be a little bit hard to read, but this is also a 2,000 gallon a minute well. In this case, we only are using empty bed contact time of 2 minutes for lead and lag systems, but the media costs quite a bit more than our typical media for our system. So the equipment cost of this system is about $1.18 million compared to the $877,000 for initial equipment. And then the operating cost for ion exchange varies really significantly. If you're doing a regenerated system, the water quality is really important. It's going to depend. That's going to determine how frequently you regenerate. And then if you're using the wheat-based anion exchange resin, water quality is also going to impact how often you have to change out the resin and the cost of those. So the initial cost for ion exchange is higher. The operating cost is going to be higher than reduction, coagulation, filtration. But we can provide you estimates for all 3 of those options if you want. And with that, I'll turn it back to Steve.
Great, thank you. So there is a Q&A system here that you type in your question, and then we'll go ahead and take those questions as they come up here. So I'll let everybody pause for a second and put in their questions.
Just to also add to that, Steve, if anyone would like to raise their hand, feel free to do that, and I'm happy to unmute your microphone.
Okay, we've got one question that's come in here. So I'll let Lee field this one. So the question, Lee, is when is RCF the right choice for Chrome 6 removal? And are there situations where ion exchange might be more appropriate?
Yeah, I think the easy answer is if you have access to sanitary sewer and you can backwash either all the backwash or the sludge from the backwash into the sanitary sewer and dispose of it that way, then probably the operating costs are going to be less expensive for that type of disposal. if you don't have a sanitary sewer on site, it's probably worth taking a look at all the options and comparing them that way.
Great, thank you, Lee. Okay, it's another question has come in here. Do you offer pilot testing for utilities before committing to a full-scale system? So I can go ahead and field that one. The answer there is yes. So we do offer pilot tests, right? We're typically booking those out about 4 to 6 weeks, depending on how busy we are. And for Chromium, typically we need a 2-day on-site time. So we get about 2 8-hour filter runs in 2 days. That's typically enough data to design a full-scale system. If we do need to stay for extra days, right, we have that capability to get more data. And then we produce a pilot report that is suitable for, gaining approval at the state level for the sizing of the system. And you can then design around that. All right, another good question here. How does the total life cycle cost of RCF compare to ion exchange or reverse osmosis for Chrome 6 removal? Lee, I think you mainly answered that IX
Yeah.
versus RCF there at the end of the presentation. And so for 1,000 gallons a minute, it was roughly $900,000 with RCF. With IX, it was about 1.1 million. But the OpEx would be much higher with the IX.
That
With
was
RO, would you be able to comment on that?
yeah, I think RO is going to be likely and maybe significantly higher than all of those options.
Yeah.
And you're going to have a brine to dispose of as well, and a fair volume of brine for that. So
yeah. So I think that's your big cost driver with RO, is that you have a liquid waste to dispose of that is fairly significant. And depending on if you can put that in the sanitary sewer or not, right, that'll be a big driver of the cost. And I've got another question here. Does ATEC incorporate the brine tank and water softening system into your design, or is that designed separately from the ATEC system for SBA? Lee, can you handle that one?
yeah, but for SBA, if you're going to do regeneration, we can provide brine tanks and pumps and control systems for it.
Great. Another really good question here, obviously, given those compliance deadlines, for California, people are thinking about this. And so the question is, what is the typical lead time from purchase order to system delivery? And so here at ATEC, right, we do our fabricating in-house, right? So we're quite efficient about this. And so we say, once we get a purchase order, we'll get a submittal turned around in 2 weeks. And then, that'll go to the engineer and the owner, right? They'll review that. Once we get that submittal approved, that starts our production process. We say that, smaller systems we can potentially turn around in about 12 weeks. Any size system we'll be able to turn around within 16 weeks. And so we just recommend budgeting probably a total of 20 weeks. So figure 2 weeks for us to get our submittal together, 2 weeks for review and approval. That's 4 weeks, and then add 16 for that production and shipping. And so you're looking at a total of about 20 weeks. A lot of good questions here, so we'll keep going. Another question here. How does ATEC handle installation? Do you work directly with the utility or through contractors? So we're the system builder, right? We integrate it. It ships out on a skid. It includes all the valving, all the piping, all the fittings. It has a control system included, and it's skidded, right? So essentially, your typical job site forklift is going to be able to pick this up, drive it over to your concrete pad, set that down. There's a good photo on the screen here, right? So you would pick those skids up, set those down, anchor bolt those. Then your contractor. So the short answer is we don't do on-site install. We just make it set up so that it's very straightforward. And so you set it down, anchor bolt it, that on-site contractor then will make the rest of the piping connections. If there's multiple skids, connect that to your well pump, set up the piping that goes to your backwash management system, connect the power for the control system as well as the wires for the SCADA, and you're up and running.
I will say some utilities have done the construction themselves rather than
Yeah.
hiring a contractor, but most of them have a contractor do it.
Yeah, true. And we mentioned earlier containerized systems, right? So ATEC can put these into a shipping container. When we do that, we're typically including your chem feed, your chem storage, your little laboratory. It's got an HVAC system. It's got lighting. So it is very turnkey. And so that can be a way to make that on-site construction more cost efficient and more time efficient. The trade-off there is certainly, a shipping container is only so big, and so you can only fit a certain size system in there. But in the Southwest and in California, as you see in the photo here, a lot of these systems are outdoors, right? They're fine. There's very little or no freeze risk, and so it would be possible. This Coagulation site, they sort of have their chem storage and their laboratory in this little building that you can see to the left of the filters. But you could also do that in a shipping container, and then have your vessels outside. That would be a way to do this very cost and time effective. It looks like we've got about 3 minutes left, so if there's any other questions, keep those coming. So here's a good question. How long should a pilot run to provide enough data for a confident design? So we say with chromium, iron, manganese, arsenic, 2 days, right, is typically adequate. We say 2 days. We're having our technician on site doing an 8-hour filter run the first day, coming back doing a second 8-hour filter run the second day. So essentially 16 hours of data is typically sufficient. And we, usually leave a buffer on the end with sites that if they have co-contaminants, right? So if you had chromium plus something else like iron and manganese, we might say, hey, let's have a third day just in case it's necessary. But by and large, those 2 days are more than sufficient.
And I'll just add, our typical scope says up to a week. I mean, if it takes longer to get the data, we'll stay and continue to test for what we need to do. And if it takes longer than a week, we'll do that too.
Yeah, and sometimes, some sites can be very constrained on backwash capacity. If that's the case, right, we're going to test some different media beds. We have some specialty media that's a little bit lighter weight, therefore needs a lower backwash rate. And so when we're comparing media columns, right, we might spend extra time to make sure we get adequate data on each column. Looks like we got another minute here, so if there's one more question. Okay, maybe not. We've addressed them all.
Yeah, I think that's we're at time, guys. So
Thank you.
Get some closing remarks. Thank you, Steve and Lee, for sharing your insights today. And thanks to everyone for joining us on the session on Chromium compliance with RCF. As a reminder, we've recorded today's webinar. We'll be sending a follow-up email to all registrants with a link to the replay so you can review the material or share it with your colleagues. If you have any additional questions or would like to discuss a potential project, please don't hesitate to reach out to ATEC team. You can find our contact information on our website or simply reply to the follow-up email. So on behalf of everyone here at ATEC Water Systems, thank you again for your time, your participation, and we look forward to connecting with you soon, and we wish you a great rest of your day.
Thanks, everybody. Have a great day.
Thank you.